In lecture 14, we will learn more basics on statistics about normal distributions and how do we analyze and understanding distributions based on a powerful plot technique called histograms. So in last lecture, we learned basic ideas about what is statistics, what is expectation and probability, and we learned discrete distributions, including uniform, binomial, and normal, and also continuous distribution functions, and these called distribution density, probability density functions. And how to use Python to generate probability distributions, use the random module, and these are Monte Carlo simulations. In today's lecture, you will learn more properties on normal distributions, because that's the most important probably in real life that you will be working with data sets, and ideas like modes, mean, median, standard deviation, and continuous distributions, how to calculate probabilities based on the distribution function, and how to test whether a data set is following the normal distribution, and how to compute and interpret the skewness of a data distribution. And we will learn a new module called Seaborn to visualize distributions of a data set, which is very handy. So understanding distributions using histograms, and this is actually a very interesting topic that you can always use interesting measures of your data set. For example, you can say, what's my mean, what's the mean, median of the data set is, and what's the standard deviation or the mode or the skewness of a data set. But these are always numbers, right? So once you get a data set and you collapse them into numbers, and you got useful information, but you also lose important ideas about what the population or the sample of the data look like in general. So histogram is useful here to bring the data back to life by showing you what the real data distributes in a parameter space, right? So the problem with the single value distributions, as we said, is that in statistics, you're collapsing a large number of samples into a measure. For example, a measure of central tendency, and we will talk about that, what that is. So here you can see it's the same mean, is just a single value that represents the center point of the data set. And a measure of variability, for example, standard deviation, measures how spread out data are. And other than that, without further information, and then you don't have a good understanding of what your data actually look like, right? So these measures are important, but they're way oversimplified. So graphing the data brings it back to life. And histogram is probably the most important thing that you need to learn about basic statistics in Python. All right, so just think about the normal distribution we looked yesterday, is that this is a function and this is the value of the x, and this is actually the probability of the x occurs here. And you can see that it follows a Gaussian function, which has an average somewhere down here at 10 and spread at 1. So this is mean and standard deviation. So two key parameters in this distribution, mean, which is the mean or expectation, and sigma is the standard deviation or spread. So the expectation equals mean exactly. That's because it's a normal distribution. It doesn't work for lots of or most of other distributions. This is the property of the normal distribution. So the deviation of the median from the mean is actually a measure of called skewness of the distribution. So in a Gaussian distribution, mu is basically calculated by averaging all the data points, and standard deviation is basically known as mathematically known as the mean R2 variation in this way. All right. So more properties about the normal distribution. First of all, it's symmetric, right? So when you see a normal distribution, it must have mean equals to median equals the mode. So we will go through about these concepts later. So mean is the numerical average, and median is the data point right in the center, 50%. And mode is the number of the data that occurs most frequently. And spread is also a useful or important property of the Gaussian, is that here's the mu, and you see the bell curve, and it looks like a bell. So outside 2 sigma, so this is mu plus sigma, mu plus 2 sigma. So outside 2 sigma, and the occurrence is basically, if you still remember, a continuous distribution function, that's probability density function. And the probability is actually the area covered by this region. So anything is above mu plus 2 sigma is basically this green area shaded here. So outside 2 sigma will have two sides, and then the occurrence rate is about 4%. So anything's deviated from a normal distribution with 2 sigma, 2 standard deviations, and it's a very small chance, 4%. And also, how do we estimate probability using a function like this? For example, this is a normal distribution. I want to see in the x-axis, average is 500. And I want to see what's the percentage or occurrence of the event x that is less than 600, which is basically this blue shaded area, right? So this shaded area means that it's the probability of an event x occur when x is less than 600, right? So in a normal distribution, and you can basically by integrating or adding all these probabilities together and get a percentage of something's going to happen or not and make a decision. And that's called decision making in data science or post data science, right? Based on how the probability, and you can predict whether something's going to happen or not happen. All right, let's take a look at a couple of examples. So this is a distribution of student grades. Let's say this is a perfect distribution. And this is mu, which is the mean score or mean grade. And you can see that's the sigma is the standard deviation. So that's 1 sigma, and that's 2 sigma, and that's more than 2 sigma, right? So you can see that everything's above 2 sigma, that's A plus. And outside mu plus 1 sigma, that's A. And within 1 sigma of the mean, that's B, and then C and D, right? So the question here, and you can see that if you remember the spreading, and these are 31%, 34%, 13%, 2% in this way. So the question, if the student distribution for exam follows the normal distribution, can you estimate how many students get A's and B's in total in terms of percentage? Which is relatively easy, right? Based on this plot. And you can see that the probability or percentage of A's and B's will be summing this blue area, this yellow area, and this green area, right? So you can see that's 34% plus 34% plus 13 plus 2 plus 0.1. So that's 84%. It's a very high percentage, which means that the exam is probably too easy, right? Okay, so let's take a look at a couple of more examples of real life data that follows the Gaussian distribution. So first one, you can see the heights of English criminals. And you can see this is actually criminals measured, 3,000 criminals measured, male criminals, and measured around 1900. And you can see that's a very nice Gaussian distribution. You don't even need this black curve to show it. And this is the weight of newborns from hundreds of thousands of babies. And you can see that most of the babies have a weight around 3.39 kilograms, and the standard deviation is 0.5 kilograms. And I think most of people falls in within 2 sigma, right? Nobody's really usually heavier than 5 kilograms or less than 2. Right? So this is the more recent example showing the probability distribution of the natural variations in the temperature anomalies from Durham, North Carolina. So you can see that the most of the variations around zero, and you have both positive temperature anomalies and negative temperature anomalies. And with the global warming effect removed based on data because the temperature actually goes up. So how you measure the anomaly is interesting, and we will talk about this in the later section called time series analysis. Right, so here you can see that in years, all the months, and you can have temperature anomalies either greater than zero and less than zero. And the statistic analysis shows that it follows a Gaussian distribution or normal distribution like that. And this is also the human blood pressure plot that we mentioned last time. Or you can see that most of the human blood pressure is between around 84 and mostly between 60 to 108. That's a very high blood pressure. So the idea is that in real life, lots of the distributions follows the normal distribution. And that's also a reason why it's called a normal distribution, right? Okay, so let's take a look at a more quantitative example of how do we use the normal distribution to make predictions or make decisions, right? So here's a very interesting example I found in college examinations. So the Tsinghua University, which is the most famous, or one of the most famous university in the Great China area, that it's really difficult to get in, right? So let's take a look at how difficult it is. So THU admits approximately 128 undergraduate students in the Guangdong province every year. So given that the total high school graduate students in Guangdong, graduates in Guangdong is about 750,000 per year, what's the odds of getting admitted by Tsinghua University in Guangdong, right? So if you don't know statistics and the answer is, that's the probability is 128 divided by 0.75 million. So that's one out of 6,000 almost, which is a very, very, very low chance. It means that, just give up, right? But it's not true because that's a good example of bad data analysis, right? So we know that everyone's different. Different students have different skills and they have different levels of studies. So the chance should be different for an individual student. So whether you use data like this to predict an individual, and then you're wrong, right? So how do we do that for individual students? And now we need data. So what data do we need to predict? And then we will need the scores of mock examinations of a particular student. And once we get that data, and we can estimate his or her chance of getting into Tsinghua University in the coming year, right? So let's see the magic. Right, for example, let's get the data. Here's Jane's mock test scores in the past year. So I did a little bit of research that the full score is 750. And then this is like a decent score for 11, 12 monthly tests per year for 12th grade. And you can see that, for example, let's assume her test score follows a normal distribution. Why can we do that? Well, you don't have to do that, but that's most likely the most reasonable assumption to make. So if we assume that's a normal distribution and we can calculate the mean, which is 6, 7, 8, and the standard deviation, which is 19 in this case, right? So based on the mu and sigma here, and it's a normal distribution, so we can make a distribution function as a function of score of Jane, right? If she's doing it with this. All right, so now let's estimate the odds based on Jane's mock score distribution, because we have learned that how do you estimate the probability of the event in a continuous distribution function. That's basically the area, right? So according to last year's statistics, if you want to get into Tsinghua University, which is really competitive, so you need at least a 700 as your admission grade to pass the admission line. So the chance of getting admitted is basically P in a normal distribution greater than 700, right? Which is basically this red area, right? So now we go into a mathematical form of table of the Gaussian distribution, and we work out this area of the red shaded area, and that's about 16% chance for Jane to get in next year. So the prediction is that she's got a much higher chance than anyone else or other people because her chance is 1 out of 6 instead of 1 out of 6,000. Right? So this is an example of how you make predictions based on the limited amount of data and also an assumption of the distribution function. Right? So that's a very straightforward example. All right, so two more things about the normal distribution of a data set you need to know is that one, the standard deviation includes about 67% of the data, which is not 95, right? So 95 will be 1.7 sigma, which is almost 2 sigma. So 1 sigma includes 67%, 2 sigma includes 95%. Right? And the second one is the mean of our samples is generally not the same as the mean of the distribution because it's you never have, because that only works when you have infinite amount of data points, and you can test that in the Monte Carlo simulations that you did. So the 95% chance bounds for the mean is related to the standard error of SE, which is SE equals to sigma over square root of n. So n is the number of samples and sigma is the deviation, standard deviation. Now you can see that if I have way more numbers, a lot more numbers, n goes to infinity and s equals to 0. So in that case, the mean equals to the mean of the sample equals to the mean of the distribution, right? So now we can take the first property and say that 95% confidence level of the mean is given by 1.797 SE. So the mean of a sample taken from a normal distribution is within 95% confidence level of 1.7 SE, right? So this means that most of the, if you take a sample from a normal distribution and the mean will be within plus minus 1.797 SE. And you can test that with the Monte Carlo simulations that you did yesterday. All right, so more important measures of a data set, and we talked about the Gaussian and the normal distribution, and sometimes they're not so normal. And a couple of concepts, one is central tendency. So central tendency, and they're commonly used ways to measure the central tendency are the mean, the median, and the mode. So mean, it's easy, just sum all the measurements and divide by the number of the measurements. And median is the value that's exactly in the middle of your data set. And mode is the most frequent value occurs in your data set, right? And so if you look at this distribution, which is a continuous distribution function, and you can see that this is the mean, which is the average of everybody in this axis, and median is the one that exactly at the 50% percentile, and mode is the one that has the highest occurrence frequency in this way, right? So the next one is called skewness, and skewness tells you how skewed the distribution function is, whether it's to the left end or to the right end, right? So now let's define the direction. So this is the coordinate system. So this is the positive direction and that's the negative direction, right? So in a negative skewed distribution, or let's say this, in a normal distribution, and you can see that the area or the number of samples on the left and on the right, they're the same in this way. So you can see that the mode, mean, and media are all the same. So everything is symmetric across that. And in the negative skewed distribution, and you can see that there's more example on the left side of the mode, and there's less on the other side. So for negative skewed, you should have mean is greater than median and then mode. And positive skewed is different. skewed towards more example on a positive direction that has the mode less than medium less than mean. All right, so how do we get information or get an idea about those important features of the data set? And then now we get back to the histogram. The histogram here, and you've already used the pandas and also PLT, pyplot, to generate histograms, and pandas is very handy, very good at handling histograms. So for example, if we have a data set, and if you still remember read CSV, and that's my data file, and print out the columns, and I have columns A, B, C, D, left skew, multimodal, IQ 10, 20, IQ 100, and etc. And then if I do the histogram of my data column A, so I do df a dot hist. If you still remember that syntax, I'm generating a histogram using the column A, and I'm setting 20 bins, and with density equals true, it's normalized to its occurrence frequency, and label it as data in this way. Right. So if you do that, and you can see that this is my distribution based on the data, which is the column A, and medium, it's right here. That's the mode which has the highest frequency, occurrence frequency. And let's put on median and mean using the function mean and using function median in this way, right? So what I'm doing here is I'm plotting a line down here from a dot median, and I draw a vertical line from 0 to 0.14, and I label it as mean. And also draw a vertical line, use a dot median, which is the median value, and draw the same line here. And you can see that the median equals to mean almost. Now, what is the property of a normal distribution? Likely. So if median equals to mean, it's very likely it's a Gaussian distribution, normal distribution. And central tendency is basically the mode. But this doesn't exactly look like a normal distribution, right? But we can have more rigorous way to tell whether it's a normal distribution. All right, so it's sometimes very useful to test whether distribution is normal or not, because if you look at the example of the college examination to make predictions, and if we know, or if we're confident about the shape of the distribution function, and you can make better predictions for things like that, right? So how do we test? And there are multiple ways to do it, and there's more mathematically rigorous way to do it. And what we do here, we'll use the normal test function from the stats module of SciPy. So SciPy is scientific Python, and stats is the module do statistics, and normal test is a function. And you can tell from the function name is that you give your data set, and normal test will tell you whether it's normal distribution or not, right? So the syntax is actually really easy. So first, you need to load the module from SciPy, import stats. Now I have the stats module. So I'm calling the function stats.normalTest, and the input is df.a.dropNA. If you still remember that, that's dropping all the lines with nans. If you don't do that, and sometimes normal test will tell you it's nan, because you're giving data points with nans, so you can't do the tests. Right? So there are two outputs, one is K2, one is P. And you can see that the P value is actually one tells you whether it's Gaussian, normal, or not normal. Right? So here we use a simple if loop, say if P is greater than 0.05, and it looks like normal, otherwise it's not normal. Right? So now if we run this code, what we get is for distribution A, the P value is 0.83. So that's greater than 0.05, and print out sample looks Gaussian, and Gaussian is normal, right? All right, so how do we interpret the results of a normal test here? So there are lots of rigorous ways to going on. So the couple of parameters explained here is that each test return at least two things. One is the statistic K2, and that's a quantity calculated by the test that can be interpreted in the context of the test via comparing it to critical values from the distribution of the test statistic. It's a it's it's a way of saying, you know, math in applied math, so it's pretty not so easy to understand. But what's more important here is the p-value. So the p-value test tells you whether it's statistically a normal distribution or not. So the rule here is that if you interpret the p-value as follows, which works nicely, and you can see if p-value is less than 0.05, 5%, reject, and the distribution is not normal. And if the p-value is greater than 0.5, you can't reject it. It's likely normal, but not exactly. So the p-value, the larger the p-value is, the better or more confident that your data sample is a normal distribution, right? So remember that above 5% p-value does not always mean the normal hypothesis is true. It means that you can't rule out the possibility that it's a normal distribution function. So if you want to, you know, as we get more and more advanced, and the p-value is basically the first step. So you need to know that if it's less than 0.5%, 5%, it's absolutely not normal, right? So up to now for this course, it's an introductory course. So let's just say when p is greater than 5%, let's say it's normal in this way. All right, so now let's try to take a look at another example of getting the central tendency from histograms using both pandas and our knowledge about distribution functions, right? So now I'm plotting two groups of data. One is from the data frame called histogram.csv. So I'm using two histograms. One is the data column A, the other one is data column B. Each has 10 bins, and I'm with density equals true, which means I'm normalizing my axis with its occurrence rate. And alpha sets the panels to be transparent and label them in this way. So if you plot this, and you can see, the first thing you see here is that you get a bunch of distributions here, but you first thing you see that this peak value is the mode of group A, and that's a peak value of mode of group B. Right? So besides group, and to get information like this, and pandas actually provides lots of useful functions to look at things like this directly. And we cannot go to all the document useful functions of pandas, but here is a useful one that you do statistics, and I want to introduce that to you here, which is called the describe function. And so the basic syntax, more information about the pandas and describe functions right here. And the basic syntax is that the name of data frame dot describe. And then you can have inputs which are set to none as default. So the describe function basically analyzes all the column data and provides a numeric and numeric estimations of its mean, median, minimum, maximum, and percentiles in this way, right? So for example, if we do the data frame df and we do df.describe, and you can see that I got a table right here, and with the column names not changed with the original names, but then the rows are changed, right? So count how many data points in here, mean, median, standard deviation of the data set A, and these are the 25 percentile from the data sets. So here, if you look at this and how to interpret that, is that, so this is basically a age. So the mean is 50, and 25% in my data set will be 48, and 50 will be exactly that mean value, and 75 will be 53.8, and the maximum value is 63.5. So describe is a simple, quick statistic results of the data table that you can look at quickly for these center tendency and other values. All right, let's take a look at another example of distribution functions using histograms, which is called multimodal distributions. And a multimodal distribution, and you can tell from the names that you have two modes, right? So, or two or more peaks in this way. So it's really easy to tell from the histogram, but you cannot tell from a single valued things like the mode, the mean, or the standard deviation, right? So sometimes these multimodal distribution reflects the actual distribution of the phenomena that you're studying. In other words, there are different peaks corresponds to different populations. And if you're using single value, and you'll be missing one, right? So here you can see you have one peak down here, the other one, and this is more obvious that you can see have one peak for Asia and the other peak for Africa. And these figures are generated automatically by the Seaborn module, and we're going to take a look at how to use it. Right. So to use the Seaborn module, and let's do import. These are standard imports for NumPy, Pandas, MPLT, and other things. And import Seaborn as SNS. So we import Seaborn, rename it SNS, and we use the SNS.distplot function to generate histograms. And here's the option said KDE equals to true, and KDE means the kernel density estimations. So here's the syntax how to get a plot like this from a data file. So file name is called gdpdata.txt, and we've worked with data before. And let's load the data file to a pandas data frame called gdp.readcsv, and generate figure, and let's filter the data first because we only want the data for year equals 2007. So this is the way how we filter the data, and we give the data frame to a new data frame called gdp.pc. And now we call the sns.distplot function here. It's the same as the pandas.hist. So distplot, and that's my data frame. And I want to data frame, I want a KDE, it's the kernel density estimation equals to true, and which gives me this blue line, and color is equals to blue and 20 bins, and I label everything in this way, right? So after you do this, so the distplot function will generate a histogram based on the data in GDP-PC, which is the GDP data. There's only one column here. And the KDE equals true will give you this blue plot showing the possible distribution function, or the kernel density function, distribution density function, and which is very convenient. And you can clearly see there are two modes down here. All right, so using the Seaborn module and with things like this, and you can easily to see whether the distribution function is skewed or not. So in real life, not everyone is a normal distribution, and sometimes they're usually skewed. And as we have learned, and this is called a left skewed function with more data points on towards the negative side, and this is a right skewed data function, and with more data towards the right side in this way. So to test whether your data sets are skewed distributions, so you can use the function called skew in this way. So it's really straightforward to do that. And let's take a look at how we do it. So the skewness of a data set left skew is basically called SK. So what is SK? So the syntax goes SK equals to stats.skew. So remember that stats is the statistic module from SciPy, and skew is the function. And I want to test a data column called left skew for skewness here. So this is the input with the data column. I'm dropping all the nans because if you're putting nans down there, and it will tell you that the skewness is probably not a number or INF, right? So these do the same thing for the data column D. And here, and you can see that for D is also another one. And you can see that for this one, and it's a left skew, and the skewness left to skew is minus 0.6, which means that it's negative skewed. And then the other data set, this one is positive 0.6, and that means it's positive skewed and right skewed. So use the skew function to test whether the distribution function is skewed or not. Right. So question, if you put in the normal distribution down here, what would be the skew value is? It has to be 0 or close to 0, right? All right. So another way to look at the different data sets is that you can compare distributions between different groups using histograms. And there are two ways to do it. And one is that, for example, in the data set, so in this lecture, and we have 4 groups of data from A, B, C, and D. And you can see the first one is we plot everything in the same plot and with the alpha value, so you can have the transparency. So it's pretty clear to see the differences between these distributions, but it's really busy, right? Everyone's clustered together, right? So the second method will just use subplots as we used before. So you can generate a histogram function for each data group, and that's A, B, and C, and D, right? So that's much more clear, but you don't have the comparison directly like this. So what's the problem of method 2? It looks fine, but what do you see? I see the problem here, right? What is the problem here? And if you look carefully enough, and what I can see here is that you will see that the distribution A, B, C, and D, they're almost exactly the same. And why is that? Because they're different on this plot. The reason is that because they have different horizontal axes in this way. So the Y limit here is not fixed. So that's also something to remember, that when you do visualization, and make sure your y-axis are the same, so you're always comparing apples to apples. Otherwise, if you look at this comparison, you will say these distribution functions are almost exactly the same, but their extension is different in y direction, right? So if you fix the y-axis down here, and you can see that now these x limit and y limit, they're exactly the same, and you can see that they're just very different distributions, as centered in different locations, has different spreading as well. Right. So last bit of this lecture is that we're gonna generate more fancy plots with the Seaborn module called box plots. I'm pretty sure box plots, you guys have seen box plots even in other tables and other statistics. So the box plots nowadays are one of the most common ways to visualize data distribution from multiple groups. And it seems like it's perfect for plotting this GDP data set we've been worked with, right? So now let's take a look at the syntax of the box plot, how you generate box plots with the Seaborn module. So we load the data and we print out the columns, if you remember that the column attributes, and you can see they have country, year, population, continent, life expectancy, and GDP per capita in this way, right? So if I want to group the data with a box plot, so the box plot function takes 2 inputs. One is the y-axis, which I set up to be the life expectancy, and the x-axis is grouped by continents, right? So now I have a plot as a function on grouped by continents and of life expectancy. And my data is basically GDP data, and with year equals 2007. So because this data set has multiple years, and if you put all the years together, and the data is really, really messy. So I'm only taking the data frame with the data of year 2007 in this way. So the box plot goes into this data frame and get the life expectancy plotted in the y direction and grouped in the x direction with the continents, right? So this is the plot you get. And you can see that now you get this nice box plot with grouped by different continents, and has the extension of the data, and that's the mean, and that's the maximum and minimum, and then that's the deviation here, down here, right? So you can also put in multiple years using the isin function, which is a membership function, if you still remember that. So GDP.year is in, I want to compare 2 years, 1952 and 2007. And then if I do Y equals to life expectancy, X is continent, and then my data frame is DF1, which has 2 years of data. And now you see that the box plot gives you this comparison of the GDP per capita at each continent and with different years, and with 1 year colored at blue and the other year colored at green, which is very handy. Right. So another one you can do with Seaborn, and sometimes people use these a lot, especially in statistics, and is that you can plot the data points with jitter using Seaborn's strip plot. So one of the biggest benefit of strip plot is you can actually see the original data points in one axis and how they distribute it in the axis here. So the syntax is similar here. So you still use the SNS, which is the Seaborn.strip plot, and year equals to life expectancy. So that's the y-axis. X-axis is continent. I'm grouping it by continent. And the data is DF1. Remember that DF1 is that the year, now the year of 2000, well, no, DF1 has 2 years here, right? So jitter equals true means I add some random variations in the X direction. Otherwise, all the points will in the same line up in the same direction. And set marker, set alpha, and that's the axis, the label, which is the year. So by doing this, and you can see that I'm generating a plot here showing the distribution of the GDP, the life expectancy for each continent, Asia, and distributed on along this axis, and with year 1952 blue and year 2007 yellow, orange in this way. And you can clearly see that after half century, and the life expectancy in all the countries almost all increased, right? And Europe has a very high one, used to start with very high one, and Asia has a very large extension, and Africa is slightly lower down here, right? So that's very simple way to do it. And also you have other options, like if you add one option called dodge equals to true, and then it's going to separate those data points, not put them overlap them together in the same direction, right? So that's how you're generating strip plots using the strip plot function of SNS. All right, so one more thing. If you put box plots and strip plots together, and then you can have actually more information about the statistics of the data set, and also the actual distribution of a data set that you're working with, right? So what we do here is we first create a box plot for the life expectancy grouped by continent of year 2007 and 1952, and give it a color pattern. And then we put the strip plots on top of each other of those box plots using SNS.strip_plot. And remember that I put the plt.show in the end, so I show everything in the same plot. So you can see that I have my box plots for the statistics in here, and also those dot plots, strip plots with the actual data points distributed along the y-axis here. So that's a very it's getting busier, but it's still very clear to see what's going on in this data set. And that's how you can generate more, put more and more information in one plot using the Seaborn module. And it's all based on histograms and statistics. All right, so let's go to the practice and try some real data.